There we go. So welcome back everybody for today's session of the Cardiff Analysis Seminar. So I see some new participants here today. So welcome to those who join us for the first time. So it's my pleasure to introduce Marina Iliopoulou from University of Kent, who today will be talking about sharp LP estimates for oscillatory integrals operators of arbitrary signature. So thank you very much for accepting our invitation, and over to you.
Thank you very much for inviting me to speak here, and thank you all for attending the talk. Today I'd like to talk about some joint work with Jonathan Hickman, and the motivation comes from the Fourier restriction problem in harmonic analysis. So the problem says, let's take a hypersurface inside Rn of non-vanishing Gaussian curvature. So this means that at every point, the principal curvatures are all non-zero. And let's take a function defined on a compact patch of this surface. Then what does its Fourier transform look like? So for this talk, it will be convenient to think of the function not as defined on this surface, but instead on the hyperplane right below. So here we have the unit ball in that hyperplane, and we think of our function being complex valued and defined there. And here I have a parameterization for the surface that I denote by sigma. Okay, and if I want to calculate the Fourier transform at any point x inside Rn, or the extension operator, as this Fourier transform is usually called, I do the classic thing. I take the integral of my function against the twist. And this twist has this phase function that is the inner product of the x, where I calculate the extension operator, with the parameterization for my surface. Okay. So there is something we do know about what this Fourier transform looks like. In particular, if we take just a little cap inside the domain, we know that the extension operator corresponding to this cap will evolve like a sum of waves pointing in parallel tubes. In particular, there is a normal right above this cap. So we can think of the function as defined in that cap with that normal. And what will happen is that the extension operator will evolve like a sum of waves, each inside a different tube, but all the tubes are congruent and pointing to that normal. So if I take another cap in the domain, there is another normal right above because of my curvature. And the extension operator corresponding to this new cap will be a sum of waves, each evolving in a different tube, all the tubes again being parallel to that blue normal. And we see that as the tubes intersect, the waves that they carry interfere with each other. So the conjecture is that this interference of the waves is so destructive that we can bound p norms of the extension operator by p norms of the original function for a very wide range of exponents, even though the extension operator is defined on a higher dimensional space. So this is trivially correct for p equals infinity. And it's easy to see that it fails for p equals 2, because for the extension operator, at every height, we have the same to norm. This is an energy conservation. So for p equals 2, the left-hand side would be infinity. So the question is, as you move from infinity all the way down to 2, at which point does this stop being true? And this is the end point we believe is correct. That's the restriction conjecture. This point is just a little larger than 2. Okay. And for, again, the purposes of this talk, it's convenient to think of everything as localized in some big ball of radius r. So for any big ball of radius r, we want to prove these LP to LP bounds for the extension operator. Well, the extension operator is only considered in that ball. Okay. So what we are proving partly is improved restriction estimates, so improved LP to LP bounds, according to the signature of this hypersurface I started from. So in particular, let's take, as we said, the hypersurface of non-vanishing Gaussian curvature. And we're looking at its signature, which means that every point we look at the number of positive principal curvatures minus the number of negative principal curvatures. And we prove improved restriction estimates when the signature is not minimal or maximal. So let's see what I mean. A classic example of a surface is like a prototypical example we're looking at is a hyperbolic paraboloid. So here the number of pluses is the number of positive curvatures, and the number of minuses is the number of negative curvatures. The extremal cases that we don't deal with are the cases of maximal and minimal signature. So maximal signature we get if we say we only have pluses all the way through, and that is the case of a paraboloid. And the minimal signature, so we would have minimal signature if all the pluses canceled out all the minuses, in which case we get a saddle. Of course, that is possible only if these omega variables are even in total. So if they are odd in total, then there will always be one leftover curvature, and the minimal signature can only be one. So according to the parity of the ambient space, the minimal signature is either 0 or 1. And as I said, we prove better estimates for all surfaces except these ones, pretty much. So in particular, we prove these LP to LP bounds with the extension operator, as we said earlier. For P even as low as these exponents, and here they depend on the signature, these lower bounds we have on P. And in fact, if the signature is even, we get this lowest P. If the signature is odd, we get another lowest P. And that fully depends again on the parity of the ambient dimension. So this was known already for minimal signature by Stein and by Burgan and Guth in odd and even dimensions respectively. And for the maximal signature case, it was done for the paraboloid by Guth and later by us for all hypersurfaces. Of course, for these endpoint cases, there are now better results than these ones I'm writing here. In particular, for the saddle, Alex Barn has better results than these ones. And for the paraboloid in R3, Hong Wang has better results than these ones. But in higher dimensions, where intermediate signature makes sense, for all intermediate signature cases, we have these estimates that are better than what was known before. Okay, and you'll see this is a bit strange that we care about signature, given that the restriction problem had nothing to do with signature. It simply said, let's take a hypersurface whose Gaussian curvature never vanishes, and we should get the same estimates for all surfaces of this with this property. So why do we even consider signature? And the reason is that we were working on another problem that actually has to do with signature, and this is just a corollary. So let's just say that the Fourier restriction problem says we saw what it says. Now, the point about it is that when you take this extension operator, the phase function it is in a product of x, where you calculate the operator, with this fixed surface every time, the same surface. You inner product against the same surface. So Harmonder asked, what happens if instead of having a fixed surface here, you have a surface that varies according to x? So here, say for this green x, we are inner producting against this original surface sigma x, but for this orange x prime, to calculate the new Fourier transform at that point, we inner product against this orange surface that's slightly perturbed from sigma x. So we can imagine mainly the surfaces smoothly varying with x. So Harmonder asked, what are the LP bounds for this kind of operator? And as long as, of course, all the surfaces, these varied surfaces, still have non-vanishing Gaussian curvature. Okay. And we do have some similarities with the general extension operator. So in particular, we still have a wave packet decomposition. If you take a single cap of your domain, then here above it, you have many normals because there are many varied surfaces. So the extension of the new type of operator, this Harmonder operator, will evolve in waves, each supported in a different curved tube. So instead of straight tubes, we have curved tubes corresponding to a cap. If we take this blue cap instead in the domain, again, above that we have many normals. So the operator will be waves carried in curved tubes, these blue tubes at Rome. Okay. And Harmander asked if we still have the exact same bounds as for the extension operator in this variable coefficient case, as long as, again, these surfaces have non-vanishing Gaussian curvature. I should say I'm not extremely precise here when I write down this phase function. So whatever I've written here is will be the first order Taylor expansion of the phase function. So we allow more general phase functions than the one that I've written here. But for now, let's just see a historical context about this problem to understand it a bit better. So Harmander asked if P can get as low as this exponent in 73. And Stein almost showed that in the 80s. So he showed that P can get as low as this other number, which is slightly bigger than Harmander's exponent. So it just has a +1 in the numerator. And that was strong evidence that the answer to Harmander's question is yes. But then Burgan showed that this is actually sharp. In odd dimensions, there are phase functions, or in other words, varied surfaces, for which the corresponding Harmander operator is not bounded in LP for any P lower than this exponent. So the answer is actually no to Harmander's question. You cannot get always P as low as this. And later, Burgan and Guth showed that you can do better in even dimensions. So you can go a bit lower, but still that is sharp. So if we study these examples, the sharp examples of Harmander operators that Stein, that Burgan and Guth produced, they correspond to varied surfaces of minimal signature. So in the odd dimension case, we have zero signature for the surface in the surfaces in that example, and the even dimension case, we have signature 1. So what we are doing with Jonathan is that we are proving the sharp LP bounds for Harmander operators according to their signature. So if the signature is 2, we show that the sharp bounds are here, they get a bit closer to Harmander's exponent. You get a bit closer again if the signature increases. We showed it all the way up to maximal signature, which is something we had dealt with Larry Guth in 2017. So this is the full picture. The closest you can get to Harmander's exponent is when the varied surfaces look very much like paraboloids. They all have maximal signature. And as you start going away from that picture, so as your varied surfaces look more and more like saddles, you get further and further away from Harmander's conjectured exponent. Okay. And of course, this problem has everything to do with signature, while the restriction problem shouldn't have anything to do with signature. So let's just see how these problems actually differ. An idea of how signature plays a role. Okay, let's take a specific function in the domain. So let's think about it as having mass that's spread out. We can even think of it as having magnitude 1 everywhere on this unit ball. What the extension operator will do to this function is that it will take its mass and spread it out in space. Why? Because the extension operator will evolve as a sum of waves, and each wave will be evolving inside some tube that points to a direction that's normal above the corresponding cap. So mainly, if you have very spread out mass in the domain, it means that you have all sorts of different normals right above, and the corresponding tubes will can point to all possible directions. So the mass is spread out in space. Now, that doesn't happen necessarily for Harmander operators. So we can start with the same function in the domain. Again, the mass will be carried by curved tubes this time. But in this case, it's possible because of their curvature, because of the curvature of these tubes, it's possible for them to essentially tile a very low dimensional surface. So these tubes can be packed along essentially this surface can have even half the ambient dimension pretty much. So these are the tubes that carry my waves, but they are still forced to live in very small space or close in a neighborhood of very small space. And because of this packing of the tubes, it means that the mass of the operator is not spread out. It is packed in small space, so it should have a lot of peaks. The operator should have a lot of peaks. And for that reason, its LP norms don't behave so well anymore, as for the extension operator, where the mass is carried far away and sort of uniformly spread. Okay, and in fact, this property that the curved tubes could have is irrespective of the signature of the surfaces we're starting from on the left. So even if you start with a phase function that gives varied surfaces that look like paraboloids, so even in the maximal signature case, it is possible again to have the corresponding curved tubes that carry the mass being packed on such a low dimensional surface. And for that reason, even for maximal signature operators, you cannot get as good LP bounds as for extension operators, where the tubes are straight. Okay, but if the signature is small instead of large, so if these varied surfaces look like saddles, you have something even worse. So this picture here is actually worse than what one may think. In particular, okay, these tubes have a width. They're quite fat. They are all equally fat. And in fact, how fat are they? If I consider caps on the left with radius r to the minus a half, so very small caps, the tubes here will have a width of capital R, of r to a half. So they are reciprocal width of the radius on the left. And my r is very big here. So since these curved tubes carry my waves, one would think that I can trace the mass of the operator all the way up to distance r to a half from this surface. But this is not necessarily true. So if the signature is minimal, it's possible for these waves that the tubes carry to interfere with each other so destructively that sort of far from this surface, you have essentially zero. They contribute zero in total. So the contribution of the waves is zero as they interfere, while the mass of the operator itself is traced only extremely close to the surface. So you could have like very, very high peaks for the operator, for the mass of the operator, extremely close to the surface, but the waves cancel each other out further out. And this means that the peaks are so high that the LP norms behave even worse than for maximal signature case. Okay, so mainly the higher the signature is of the varied surfaces on the left, the more this phenomenon is prevented. So you have this surface close to which your tubes are clustering, but you have that if the signature is intermediate, so it's higher than zero, then in some directions transverse to the surface, you have some, as we call it, equidistribution of the operator. You still find waves if you look far from the surface up to distance r to a half. While in other directions, you'll still have zero contribution within this distance. It's only within distance 1 from the surface that you'll find waves. So I'd like to just demonstrate this a little bit, and I can even explain it for the paraboloid and the saddle cases. It doesn't have to be, in other words, varied surfaces. Even for fixed surfaces, this can be seen. So let's look at the paraboloid in R3. Here it is. And I'm in a situation, I pretend, where my wave packets are clustering indeed very close to a specific surface variety. So here I'm getting a plane. That is a surface where I pretend my tubes are clustering. And what I want to show is that because I started with a paraboloid on the left, I will have that this extension operator in this case is equidistributed up to some big distance transversely to this plane. Okay, so let's see. This kind of equidistribution will come from an uncertainty principle. So I need to understand a function that gives rise to these wave packets, where it is localized in the domain. Okay, so let's see. Mainly I need to find the caps that these tubes are coming from. So let's look at the cap to begin with. What tubes could it give rise to? So those tubes it gives rise to are parallel to the normal above. And and that normal is parallel to this vector omega1 omega2 minus 1, because that's what I get. I get omega1 omega2 if I differentiate, if I take the gradient of my defining function here. Okay, so if I parameterize the directions of the tubes in my plane by omega1 omega2 minus 1, then I can view those directions as this line at height minus 1. So I'm only looking at the corresponding caps, in other words, at the omega1 omega2. So since omega1 omega2 minus 1 is forming a line, the omega1 omega2 also form a line on the left that passes through 0. In this case, I have this vertical plane I drew through 0. And therefore, any function that gives rise to these tubes on the right will be supported on this y-axis in this case. So you can even visualize it as defined on the slice right above this line. So these are the caps with normals, the same ones as the ones on the right. So indeed, any function giving rise to these wave packets will be localized on the left in such a shape. So in other words, it lives on the same plane as we started from on the right. And for that reason, some uncertainty principle ensures that transversely to this localized space, we have a good distribution of the Fourier transform. So we can, it's not very hard to say that we have a good distribution of the Fourier transform or extension operator in directions transverse to this plane on which the function is localized. And in other words, transverse to the original plane we started from. By this, I mean that if I move even far outward, transversely to my plane, I will still be finding part of the mass of the operator. I will not be getting 0, or be getting something that contributes its fair share all along the way. And even if the original plane was tilted, I would still have something similar. So again, I draw the line of directions that are of wave packets on that plane. The corresponding caps, again, live on this line that's parallel to the one on the right. This line is off 0 now, it doesn't pass through 0, but in any case, it's still a line, and the wave packets and the caps come from the slice of the paraboloid right above. These are here is the domain of any function that could give these wave packets on the right. It's still localized, similarly to before, on a vertical plane. So transversely to this plane, I will have a good distribution of the Fourier transform. Now, this plane, of course, is not the same as the one on the right, but still, since I have horizontal equidistribution, I can see that I can also have like equidistribution in the diagonal to an extent. So this is a moral of why, indeed, if you have wave packets clustering on a surface like a plane, you have the Fourier transform being, the operator itself is equidistributed transversely to that surface. The situation is extremely different if you start though with a saddle in R3. So here it is, the defining function can be omega1, omega2. Again, I take, in this case, I will take the ZY plane and I will pretend that I'm in a situation where my wave packets are clustering on that plane. I want to see what functions such wave packets can come from. So let's see, a given cap, what normal does it give rise to? What tubes can it give rise to? Well, the normal is the one right above. But in this case, the first two coordinates are flipped. So if I take the gradient of the defining function of the saddle, I get omega 2 minus omega 1 instead of omega 1, omega 2. And that will make a big difference this time. So let's see why. Let's take the directions on the right and parameterize them again in the form omega 1, omega 2 minus 1. So the directions are again parameterized by this line, which is parallel to the y-axis in this case. However, the caps I'm looking for now that give rise to these directions have flipped coordinates. So actually, they form the x-axis, not the y-axis. So a line transverse to the previous one. Therefore, here are all the functions, here are localized all the functions on this red line that give rise to the wave packets on the right. All these functions are localized, in fact, on this line or on this plane here, and they have a good distribution of the Fourier transform transversely to this new plane now. So I have a good distribution transversely to this plane on the left, or in other words, a good distribution parallelly to the plane I was aiming for, not transversely to it. So I get a good distribution in the wrong directions, in other words. So this flipping of coordinates that happens every time your defining function has a signature 0 part doesn't allow you to have this good distribution transversely to where the wave packets are localized. And that can make things bad. In the curved tube case, it can be responsible for many, many bad phenomena. Okay, now if you have intermediate signature, then one part of your defining function will look elliptic. The other part will be bad, it will be hyperbolic, but from the elliptic part, you can get some nice directions along which you have a good distribution. So the Fourier transform can have many high peaks in some directions, but it will be quite mild in different directions, in some other directions. All right. So that is one way in which signature plays a role in this problem. But it does play a role once more. So I'd like to explain that as well. And that has to do with our process to prove our estimates. So the method we follow is we first prove some other estimates that we call multilinear. We see what those are about. Then we plug those into a method developed by Bourgain and Guth. And that kind of method immediately transforms multilinear estimates into linear ones. By linear, I mean of the type we want for the operator itself. LP to LP bounds for the operator. And what happens is that the multilinear estimates are sensitive to signature, and so is the conversion process. Okay, so let's see what I mean. What do I mean by multilinear estimates? And even for the extension operator, this works here, what I'm going to say. The idea is you have a surface on which your function is defined. So what we want to do is to split this surface in smaller caps and understand the contribution from different caps at the same time. So if we just have here K transverse caps, as we say, so meaning by transverse, what do we mean? We mean that their normals will form a K-dimensional space, will span a K-dimensional space. So let's say we have K transverse caps and K functions below defined on these caps. What can we say about the contribution to the extension operator from these different caps? So multilinear estimate looks like this. It controls the geometric means of the contributions of the different K caps. So at every point, you calculate the extension operator coming from the K caps, and you take the geometric mean at that point. And you want to control P norms of these geometric means by geometric means of the two norms of the original functions. Okay, so the conjecture, which they have adapted, so this was a conjecture for the maximal signature case, and we adapted it in the general signature case. The conjecture is this. You don't need to know what it says, but the question is how low can P get? And the conjecture is that this is how low they can get exactly. And that how low P can get depends on the level of multilinearity and on the signature. So for low levels of multilinearity, meaning you have very few caps, few transverse caps only that you consider, you get only as low as here. That is quite a high exponent, unfortunately. While if you, as you start increasing your transverse functions, you go and you achieve better and better P's, lower and lower P's on the left. So part of this is known. The worst case scenario is known by Stein's estimate. Maybe you remember this exponent, twice n+1/n-1 from the historical context page. So Stein showed this for all Harmonic operators, in fact. So you can work this out for the geometric mean by Hölder's inequality on Stein's standard linear estimate. Now, the other extreme, where you have high levels of multilinearity, so many transverse caps, this was done by Bennett, Carberry, and Dow. And the middle range is unknown, but we sort of proved it with a weaker left-hand side too. So our left-hand side is not really a p-norm, it's something else, but it is still good enough to plug into the Bourgain and Guth method and get linear estimates out of it. So what I find very interesting for this is that these multilinear estimates are signature sensitive, even for extension operators. So while the restriction problem itself should have nothing to do with signature, where you have LP to LP bounds, when you have L2 to LP here for multilinear estimates, signature plays a role even for extension operators. And I'd just like to explain a little how. So how would they create a sharp example for the middle range? So let's see. So what we'll do is we tensor out examples that correspond to Stein's bad exponent. That's a very high exponent, with examples that correspond to the Bennett-Carberry Tau exponent. And the Stein exponent will come from saddles, studying saddles, while the Bennett-Carberry Tau exponent will come from studying any surface we like a paraboloid, for example. So if you have intermediate signature, you tensor out like an example that corresponds to the saddle part of your surface with an example that corresponds to the elliptic part of your surface. So let's see what I mean by that. If I have an elliptic scenario, or actually I shouldn't be calling it elliptic, because what I'll say here, I can create an example like that for any surface, but I want to contrast this with a strictly saddle example that I'll talk about later. So let's say we have a paraboloid. Let's say I want to create a bilinear example that satisfies the Bennett-Carberry Tau exponent. What I'll do is I'll take two caps because I'm going for a bilinear estimate. So in other words, two functions here with two different normals above. And I'll make sure that the wave packets coming from the red cap will tile a plane, a two-dimensional plane. And the wave packets coming from the blue cap will tile the same plane. So that's a way to create a bilinear example that actually satisfies the Bennett-Carberry Tau exponent. If you wanted a trilinear example, you'd get a third cap with a new transverse normal, and you'd make sure that the tubes coming from the red cap will tile a three-dimensional cube. Same for the blue cap, same for the new cap. Anyway, these are quite simple. But when it comes to the saddle, we have another type of example that cannot go that does not satisfy such good estimates. So let's see, here is a saddle. And to create a new type of bilinear example, I'm going to use that the saddle contains lines. So here, I'm going to take two, not caps anymore, but slabs. They have constant length, but they're very, very thin. So they essentially live on the x-axis. And they have different normals here. So indeed, whatever comes out of that will create a bilinear example. So what I want to show is that in a big amount of space, the geometric mean of the geometric average of the extension operators of the two things will be very large, while the two norms of the functions are small. So my functions will be the indicators of these caps. So let's call H the indicator of the blue cap. And then I want to understand a little its extension operator. I want to show that this extension operator is actually big on some big part of the space. So what we have is that the omega variables, the variables of H, are very restricted here, right? So omega 1 is at most a constant. Omega 2 is much, much smaller. And of course, because of that, their product is also very restricted. So these are tiny in some sense. And therefore, if my x1, x2, x3 live in reciprocal dimensions, so x1 is at most a constant, x2 is at most small constant times r, x3 is at most again small constant times r, then if I make sure that my constants hiding here are small, this phase function can be about 0, can be very, very close to 0. In other words, I will, on that part of space, on this big red box for the x1, x2, x3 coordinates, the phase function will contribute nothing. It will be practically 0, and they will have no oscillation in that big box. In other words, on that big box, here the red box, I have that the extension operator is very large. It's essentially the integral of H, like as if the e to the 2 pi I blah blah didn't exist at all. So by large, I mean bigger than the integral of H, which is r to the minus 1. And at the same time, the 2 norm, which should be on the right of the restriction estimate, the 2 norm of H is very small. It is the square root of the size, of the blue size. So at most this. And of course, the same stuff holds for the indicator of the green slab. There's nothing special here about the blue slab. Whatever I used in this analysis holds for the green slab as well. So if G is the indicator of this green slab, the same stuff holds for it. So in the same box, the extension operator of J is also very big. So their geometric mean, the geometric mean of the two operators should be very big. While on the other hand, the 2 norm of J is still very small. So the geometric mean of the two norms is very small. And you can see if you plug, if you try this out, that you cannot go any lower than Stein's exponent for this example. So if by the way you wanted to create a trilinear example here, you wouldn't be able to add a third slab along the x-axis because whatever normal that third slab would have would be spanned by the previous 2 normals, the blue and the green. So you'd have to find a slab, a cap, say, that's somewhere else, and it would have to be more of the Bennett-Carberry tau type. So as your multilinearity increases, you're forced to involve the Bennett-Carberry tau examples in your picture. Anyway, so what I want to say is that signature plays a role here in multilinear situation. And just to finish off, it's not just that it plays a role in the multilinear estimates. The way you change those into linear estimates, Bourgain and Guth method, is also signature sensitive. So let's see what I mean by that. We said that the point of the Bourgain-Guth method is to take the surface, chop it up in smaller parts, and understand the contribution first from transverse caps. That is done by the multilinear estimates. Once we do that, then at some point we have to understand the contribution from caps that are not transverse. So in other words, from caps that live like this on a slice of our surface. So you see all the normals here in this picture to these caps are drawing out a 2-dimensional plane instead of a 3-dimensional space. So you see examples like this, we have to understand at some point. So in other words, we have to understand the full extension operator in terms of its parts that are drawn out in this picture. And this is done by decoupling estimates, which this is essentially what decoupling is. It takes the full operator and understands it in terms of its parts that live on different bits of the paraboloids. And these decoupling estimates, though, become more interesting, more useful, the more curved the slice is. So these are more efficient with curvature. So you see here, I took a slice of my paraboloid, and indeed this slice was curved. That's very good. It means I will have a very nice decoupling estimate. However, if I had a saddle instead of a paraboloid, a slice could be a line, in which case there is no interesting decoupling estimate. I get a trivial decoupling estimate there. So whatever I get out of the Bourgain-Guth method for a saddle cannot be as nice anymore. The point is that the higher the signature is of the big surface, the more you're ensured that your slices will have curvature. So if you have mixed signature, then and you take a high dimensional slice, it's very likely that it will have some non-zero curvatures in it, and therefore the decoupling estimates won't be that trivial. So higher signature gives better estimates through this conversion, Bourgain and Guth conversion. All right, so this is what I wanted to say. This is how signature plays a role. I guess I'll finish by explaining what the Harmonic problem really is, what the Harmonic operator really is, because I didn't really say that. I gave some sort of general phase function, but I said that's not really true. It's just a first order Taylor approximation. So let's just see a dictionary that will get us from a general extension operator to a Harmonic operator. Right, so we said that we will be thinking of our X, like the domain of the operator, always being a big ball of radius R. So we want to incorporate that localization into our operator first. So what we'll do is we'll think of a cutoff function on the X variables and on the omega variables here. So on the unit ball over n cross the unit ball over n minus 1. And we want to, so for the X variables to live in a big ball of radius R, we want to divide X by R in here in the operator. And this restricts X in that big ball. And of course, the omega, the domain of F, is restricted to be the unit ball in Rn minus 1 in the hyperplane below the surface. Okay, and this X over R, I want it to appear in the phase function as well. So go in the phase function and I divide by R and I multiply with R outside. So what happened? The original phase that depended on X and omega, I could see it as the inner product of X with sigma on the unit balls of the corresponding spaces. But as soon as you divide with R inside and multiply with R outside, X is localized in the big ball of radius R, and that is the new phase function. That is the phase function I have. I call it phi R. Well, a Harmonic operator will have a much more general phi R of the same type as its phase function. So what happens is that instead of this specific phase function, this inner product thing, for a Harmonic operator, I put a much more general phi R that, however, follows in a similar way. So instead of having a very specific phi, I have a more general smooth phi defined on the unit ball of the two spaces. And then phi R comes from it the same way. Inside phi I divide X by R, and outside I multiply with R. And of course, the cutoff function is the same as before. So X still lives in a big ball of radius R here. Okay, and I said, of course, that there should be some connection of this phase function for the Harmonic operator with some surfaces, some varied surfaces, unlike on the left where I have fixed surface. So let's see how surfaces come out of this phase function. Well, how does the surface come out from the phase function on the left? It comes up if you differentiate your phase on the left with respect to X. So if you take the gradient with respect to X, you recover the fixed surface on which everything is happening on the left. So on the right, that's how we defined our varied surfaces. We differentiate with respect to x, our general phase function. And for any then given x, that is the varied surface that will correspond to that x. So Hermander asked if these things, these sigma x, defined in this exact manner, are hypersurfaces in Rn of non-vanishing Gaussian curvature. Does the Hermander operator satisfy the same LP bounds as the extension operator? That was the original question that we are answering. So Hermander's conditions on the phase function were on these surfaces were very, very simple. The first condition was that these surfaces have to be hypersurfaces, which means that if you take the tangents at any point, omega, those should span an n-1 dimensional tangent space. So we want these tangents to span such an n-1 dimensional tangent space. This first condition by Hermander simply meant these sigma x were hypersurfaces. And to have them of non-vanishing Gaussian curvature on top of that, you need to just take the second fundamental form at any point omega for any one of these sigma x and have that thing is non-zero. So these were the only two conditions that Hermander imposed on his phase function. And this, as we said, were not enough to give the same LP bounds as for extension operators. What we are proving is that if we do have a phase function with these two conditions by Hermander, then the best possible estimates that you get for your Hermander operator depend on the signature on these varied surfaces. So at every, so we're looking at the number of positive eigenvalues of this second fundamental form minus the number of negative eigenvalues at any point, and that is the signature of any one of our varied surfaces. And according to that signature, we get the best possible bounds for the operator. Okay. This is what I wanted to say. Thank you for listening.
All right, thank you very much. Thanks for the nice talk. So do we have questions for the speaker? So.
Well, I have a question. So throughout you assumed that the surface has non-vanishing Gauss curvature everywhere, right? So is there anything that can be salvaged if you have points, maybe a small set, I mean low dimensional set of points where the Gauss curvature actually vanishes?
Yeah, that's a very interesting question. So there is work by Detlef Müller, Anna Vargas, and Stefan Busenenke on that topic. Even if you have one flat point, things become very difficult. So yeah, you have to be very careful about how the derivatives change closer and closer to the flat point.
All right. Thank you.
Thank you.
So are there any further questions? So maybe I'll ask something quick. So in this last slide that you're showing, this sigma is a constant, right?
Yeah, it is. So because you're looking at the compact patch of your surface, we're mainly pretending that everything is this. Yeah, these things don't change. Like you would have a flat point if it changed or something.
Mm-hmm. So and can you deal with cases where somehow the signature changes? So it is a function in various points of your surface, or is that?
I think this would essentially be very similar to the previous question.
Mm-hmm.
It would become very complicated.
I see.
And we don't deal with that, no.
So it becomes complicated in the case where it becomes zero, yes? Or...
Yeah, where one of the signatures becomes zero, where you have a flat point somewhere. things become complicated. But there are things to do, though. I mean, this is relevant, but not exactly what you asked. If you still have some of the curvatures being 0, but everywhere the same number. So if you have like a cone, so things were done very, like 2 weeks ago. Someone, Robert Schipa, wrote a paper where he involves like constant signature, but some of the curvatures can be 0.
I see.
Yeah.
I see, but they have to be somehow, yeah, constant throughout.
Yeah, it's okay. I mean, for Hermander's problem, it's fine. Like it's not like an assumption we're making. It comes out of the problem that this thing is a constant. But for, of course, it is very interesting to see what happens, even for extension operators when you have flat point. And I would direct you to work by Detlef Müller and others on this. Yeah.
I see. Yeah, I get the general idea. Thank you very much. Any more questions for the speaker?
Maybe I'll ask a quick question. So if you replace your paraboloid by something that sort of asymptotes to something that is almost flat, then what happens?
Same problem. So our domain is a compact set mainly. So you don't have this problem. If you let it go to infinity, then of course you essentially get flat points. So it is equally hard. Yeah. And I think you'd have to chop it up in parts where your normals are within some range, and then work with each part and try to collate them together. But yeah, it will be very difficult. And also these techniques we're using here, we sort of reduce the case. So you have to start, you can start with a phase function, but then at some point you have to do some transformations and you get to other phase functions from your original one. And therefore, you want to have some uniform bounds, like eventually reduce the family where there exists some uniform bounds across the whole family. And I don't know what would happen if you allowed all these surfaces to have curvatures going to 0, essentially. Yeah. It would be a completely different issue.
So, okay, maybe I'll ask one final question, if I may. So is anything known about the topology of the space of this phase function satisfy these properties?
Topology, meaning what do you mean?
Is it path connected or?
Ooh. So what?
Somehow, if you use somehow non-degenerate phase functions in the usual way for oscillatory integrals, you have some information about the topology. I was wondering whether anything is also true here.
I don't know that part that you just told me. I don't know.
No problem. Yeah.
Our phase functions satisfy exactly these 3 things, like H1, H2, and all of them have the same sigma. But I don't know anything about topological
okay. No
issues with this. Yeah, sorry.
Thanks. Okay, if there are no further questions, let's thank the speaker again for the very nice talk. Let's